Okay, so we've seen so far we've seen several gas laws. We've seen Boyle's law, which is P1 V1 is I'm sorry, PV is equal to a constant. We'll just write them in terms of constants for right now. So PV is equal to a constant. We've also seen Charles's law, V over T is equal to a constant. We've seen the P2 relationship, Montan's law, P over T is equal to a constant. And then we've seen Avogadro's law, V over N, being equal to a constant as well. So what we can actually do is we can take all of these individual gas laws that relate just two variables, and we can now combine them, combine all of these into what's known as, and this is not very fancy, the resulting gas law is called the combined gas law. Okay, it's not very inventive in terms of the name, because all we're doing is combining. And when we combine our these different parameters, right, what we end up with is the following. We get PV over N times T is equal to a constant. Right, and if you look at this combined gas law, it actually has all of the other gas laws in it. So for example, if we are keeping the amount N and T constant, so we can ignore those terms, we can move them to the other side, right? Then we end up with PV equals a constant, which is Boyle's law. Okay, so Boyle's law is there. If instead we wanted to keep the pressure and amount constants, so we move the P and the N over to the other side, then we end up with the V over T relationship. That's Charles's law. If I wanted to keep the volume and the amount constants, so V and N, so I ignore these, move them to the other side, then I have P over T equals a constant. That's a Montan's law. If I wanted to keep pressure and temperature constant instead, okay, so these two, well, then I end up with V over N equals a constant. That's Avogadro's law, right? So it's got all of the laws in it. We just need to know how to interpret what's happening. So again, PV over NT is equal to a constant. It's just a combined gas law. The way that this is going to be useful to us, again, is if we relate initial to final conditions. So we can say P1 V1 over N1 times T1 is equal to P2 times V2 over N2 times T2. In most cases, not all, but often what we are working with is constant amount of a gas. So in other words, N is held constant. So we can then ignore the N here. And what we end up with is the generic or the normal way in which the combined gas law is shown, which is P1 V1 over T1 is equal to P2 V2 over T2, right? If you look in your textbook and other places, this is usually the way that the combined gas law is written, but it can also be written this way if we're looking at changes in the amount as well. In most cases, we're not changing the amount, N is held constant. That's why we can ignore it in the other form. Either way, the combined gas law can be used when we have several different parameters to work with in a question. So let's take a look at an example of where we can use this, this combined gas law. So it says if a child releases a 6.25 liter helium balloon, so right away we have a volume here. So let's write this. This is V volume being equal to 6.25 liters. Parking lot of an amusement park where the temperature is 28.5 degrees Celsius. So this is a T, 28.50. Okay, right away convert it to Kelvin. Don't wait until the end. Okay, and then the air pressure is 757.2 millimeters of mercury. That's a pressure, 757.2, and then meter G. says, what will the volume of the balloon be when it has risen to an altitude where the temperature now is negative 34.5. So this is a new pressure. So we can call this P2. I'm sorry, a new temperature, T2. So that means the first temperature given would be T1. So this would be T2 negative 34.35 degrees Celsius. And then the new pressure now, this would be our P2, would be equal to 366.4 mmHg. And what we needed to find here, asking specifically what will the volume of the balloon be, what we need to find, our unknown is our V2. That is our unknown in this problem. And we're given volumes and temperature. We're given an initial volume, initial temperature. We're given an initial pressure as well, given the final temperature, final pressure. We need to find the final volume. So obviously here, we're not given any information about the amount, N, so we can ignore that. So what we're going to do is we will use our P1, V1 over T1 equals P2, V2 over T2. Okay, and what we need to solve for in this equation is our V2. We need to isolate this on one side of the equation. In other words, solve for V2. And there are several ways you can isolate V2 on one side, depending on how you've done algebra before, how you manipulate your equations. Whichever way you use it, you'll need to end up with the same answer. So there are a couple approaches to this. We can cross multiply if you're familiar with cross multiplication. If I cross multiply this way and I cross multiply that way, right, what I get is P1 times V1 times T2, as I move this over here, would be equal to P2 times V2. Then I move T1 over times T1. And now, right, I want to just get V2 on this side. This is my unknown. I can divide the right side by P2 times T1. So these cancel away. Whatever I do to the right side, I need to do to the left side as well. I need to divide the left side by P2 and T1. So what I end up with is P1, V1, T2 divided by P2 times T1 is equal to V2. So I've isolated V2 on one side. I can just substitute all of these values now into this equation and solve for my unknown. Remember, you want to make sure the key thing here is your temperature in Kelvin. You need to convert that to Kelvin before you start plugging your numbers in. Okay. So if we rearrange the equation, right, we end up with exactly what we just wrote out. Our P1 times our V1 times our T2 divided by the P2 times the T1. We solve for it and we end up with 10.2 liters as our final volume. So again, the approach here is very similar to the example we did with Boyle's law, the PV relationship. The only difference now is we have an extra variable to contend with on either side of the equation. It does add another layer to your algebraic manipulation, which is why you need to make sure that you're able to rearrange these equations fairly quickly, okay? You shouldn't be spending 10 minutes trying to isolate V2. If you have trouble doing this, come see me. You can go to the tutoring center on campus, but you need to be able to do this, okay? Rearranging equations, using algebra to solve, that is very, very, very important. And a lot of the gas laws are going to involve that.